Okay, so what we're going to talk about now is we're going to take a graphical approach to last section where we talked about functions, and then we're going to basically get into how we would define them graphically. So let's start off with talking about the graph of a function. So how do we describe this? We would say that if f is a function with a domain of A, then the graph of f is the set of ordered pairs that looks like this. Is the set. Now I don't know if you've seen set notation, but we're saying this is the set of all points where x is my input, f of x is my output, so these are my x and y's. I'm just literally plotting them one by one, such that x is in A. So if you haven't seen this notation, this weird looking E is just saying x is an element in the domain. So basically what we're saying is you take all your input values, you find their outputs, you find the ordered pair, you plot them, and that's basically what the graph of your function looks like. So this is plotted in a coordinate plane. Okay, so let's talk about the first visual test that we do, and I'm sure you've heard of this, which this is called the vertical line test. And what the vertical line test does is you use this to pretty much check to see if the graph of something represents the graph of a function, right? So we would say that this is a way of checking to see if graphs of relations are functions. So let's define what the vertical line test is, and then we'll make sense of why that's the case, or visually why that works the way it does. So by definition, we say that the vertical line test. So this says a curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. So basically what we're saying is if you could find a vertical line that intersects the curve more than once, then it's definitely not a function. If you can't, then it is a function. So let's look at our first example where we're going to say use the vertical line test to determine which curves are functions. Okay, so let's look at a bunch of these graphs. Okay, so here are the 4 graphs. So let's take a look at this and see which ones of these represent the graphs of functions. So this one, if we look at A, no matter how many vertical lines I draw, each vertical line intersects the curve no more than once, which means this one is a function because it doesn't fail the vertical line test. Now, over here, if we look at this one, this is clearly not a function because I could find one vertical line, and there it is, where it intersects the curve more than once. And hopefully you see why this fails the definition of a function, because remember what we said in our last lesson is if an x value produces more than one y value, or each input produces more than one output, it can't be a function. So look at what this is. If I draw a vertical line, the x value doesn't change. So for this x value, this produces 3 different outputs, which in other words, that means that this is not a function. So this is not a function. How about this circle? At this point, I think it's clear to see if I could draw a vertical line, intersect it more than once. So we'd say that this is not a function. And then this last one, if you look at it, no matter how many vertical lines I draw, each vertical line will intersect this at most once. So this one is a function. So that's also a function. Okay, so moving on to determining if equations represent. So what we're going to do now is we're going to determine if equations represent y as a function of x. So if I want to check and see if an equation represents y as a function of x, what that means is I should be able to solve for y in terms of x. So that's literally what we're going to be doing. So when asked to determine which equation represents y as a function of x, we basically try to solve for y. And when we solve for y, we want it to be in terms of x, and that's if needed, right? So sometimes it might not be, sometimes it might already be in terms of x, but solve for y in terms of x, then determine if each input has one and only one output. Because if it does, then it's definitely a function. If it doesn't, then it's not a function, right? Because remember, we want to represent y as a function of x. So since we're calling it a function, we want to make sure that it does not have, each input doesn't have more than one output. So let's look at our second example, and we'll be checking that here. So we're saying, does the equation x squared plus y squared equals to 8 define y as a function of x? So if we check this, we start off with x squared plus y squared equals to 8, and we solve for y. So if I'm solving for y, I subtract x squared from both sides. So what does that give me? Y squared equals to 8 minus x squared. Now to solve for y, I have to take this square root of both sides, and what do I get? Y equals to plus or minus square root of 8 minus x squared. And see, this is y is not a function of x. How come? Reason being, if you look at this, for each input, no matter what x is, I get two outputs, right? At the very least, the plus or minus. So for instance, if x is 0, I get y as plus or minus rad 8, which, since for each input I'm getting more than one output, this is not a function of x, okay? So the last thing we're going to do is we're going to talk about some important functions that we need to know the graphs of. And you're going to notice that we're going to use these a lot throughout the years. So if you don't know them by now, I think you already do know them. But these are some important functions that we are going to be talking about throughout the entire year. And even in calculus, you'll encounter these. So important functions to know the graphs of. So there's 6 of them we need to know. So the first one is the constant function. Okay, so it's the constant function, which then says f of x equals to b. So we know that constant functions are going to be horizontal lines, and this is a y value of b. So what we're going to be doing now is
what's your login?
So the next function that we need to know is the linear function, which these you all know. These are basic lines. Which is f of x equals to mx plus b. So we know that this is in slope-intercept form, and my y-intercept is b, and whatever the slope is, it'll tell me how steep it is. Okay, so let me get a new sheet of paper. So the third type of function is known as the power function. So power functions look like the form f of x is equal to x to the power of n. Now, I'm generalizing this because we know that, and we don't want, when n is 1, we want to talk about greater than 1, because power functions, we want n to be greater than or equal to 2, and it's we want it to be an integer as well. So if n is 2, for example, we get f of x equals to x squared, which is our parabola, right? When x is 1, y is 1, negative 1, 1. We get our classic parabola. If n is odd, we get the cubic function, which looks like that. And then when n is even, so if I have f of x equals x to the power of 4, this looks like the parabola again, except what happens is, so for the parabola, notice how from 0 to 1 it's not as flat. Since this is a higher power, between 0 and 1, anything to the power of 4 makes it a little flatter, and it increases faster. It's a little flatter. So in fact, all of the even powered functions look like parabolas, except the larger the number. So if this were x to the 6th, it would even be flatter between 0 and 1 and negative 1 and 0. And then f of x equals x to the 5th. What would it look like? It would look similar to x cubed, except between 0 and 1, it would be flatter. And then negative 1 and 0 and negative 1, it would be flatter. And then after 1, it would increase and decrease faster. So these all look the same, except notice how this is more flat between 0 and it increases faster. Okay, so those are the power functions we need to know. And by the way, I'm not going to go any further than this. Like x to the 6th looks like that, except it's flatter and it increases faster. X to the 7th looks like this, but it's flatter here and it increases faster. So the larger the exponent, the flatter it is between 0 and 1, and then after 1 and negative 1, it increases even faster. Okay, so let's go on to the reciprocal function. So the reciprocal functions basically are also of the form, there's different formats of them. So let's start off with the most basic reciprocal function, which is f of x equals to 1 over x. And see, if you remember, 1 over x, at x equals 0, we had a vertical asymptote. How come? Well, vertical asymptotes mean where the function is undefined. So clearly we know x can't equal to 0. Now look at what happens. If x is 1, if I plug in 1 there, y is 1. If I plug in 2 there, y is 1/2. If I plug in 3, y is 1/3. So what is it that we notice? As we go to the right, this gets closer and closer to the x-axis. It doesn't really touch the x-axis, it just gets closer. Now what happens if I get close to 0? If I plug in 1/2, that becomes 2. If I plug in 1/3, that becomes 3. So it goes upwards. Okay? Now on the negative side, it does the same thing. If you go to the left, it gets closer to 0. If you go to the right, it goes down forever. And just visually speaking, anytime a graph gets near a vertical asymptote, it either always goes up forever or down forever. So that's what f of x equals 1 over x looks like. Now what would it look like if it was f of x equals 1 over x squared? It would look similar to this, except since it's x squared, all my negatives would become positive. So once again, if I plug in 1, I get 1 here. And this is a vertical asymptote again at x equals 0. And then what do we notice? As we go to the right, this increases or goes to 0, and it goes to 0 faster than that does because of the x squared. And then it also increases upwards. Now, when I plug in negative 1, notice how when you plug in negative 1 for x squared, negative 1 squared is 1. So it puts you back up. So that's how this looks. Okay? So, and here's what we could say. How would f of x equals 1 over x cubed look like? It looks similar to the odd powered ones. In the negative x values, you're going to have negative outputs. So it'll look similar to 1 over x, except what will it do? It'll go up and down faster than 1 over x. So what would 1 over x cubed look like? It would look something like that and like that. Vertical asymptote. Negative 1, negative 1. It would go down like that. Okay, so there's the 1 over x cubed. How about f of x equals 1 over x to the 4th? It would look identical to 1 over x squared, except the only difference is since there is a higher power, it would increase faster and decrease faster. It would increase faster and decrease faster than that. Okay, but other than that, anytime we have a reciprocal function, 1 over x to the odd power will look like this. 1 over x to an even power will look like that. Okay, so that's kind of what our reciprocal functions look like. Okay, now moving on to our next one, which is the absolute value function. which we know looks like f of x equals to the absolute value of x. And if you remember, this kind of looks like that v, doesn't it? Because we just want x to always be positive. So at 0, it's 0, 1, it's 1, negative 1, it's 1, and it looks like that. Okay, so that's our absolute value function. And the last thing that we're going to talk about is the greatest integer function, which is defined as follows. Now you may have seen this last year, I'm not sure if you did or not, but it looks like this. It's known as the step function. Okay, so the greatest integer function, the best way to think of it is, I think of it in terms of, like, by definition, here's what it means. The greatest integer function means, so this is asking us, what is the greatest integer less than or equal to x. So what I want to do before we create the graph of this, let's ask some questions here. See, if I were to say, hey, what if we have f of 0.1, which is 0.1. So when you put this in there, the question becomes, what's the greatest integer less than or equal to 0.1? So think of it this way. The way I think of it is this. I say, look, what are all the integers less than 0.1? As far as integers go, it's 0, negative 1, negative 2, negative 3, and so on, right? I made a list of all my integers less than 0.1. Now, from all of these, what's the greatest? It's 0. So 0. Now, what if I did this, f of 0.2? 0.2. What's the greatest integer less than or equal to 0.2? Once again, it's 0. In fact, from 0 all the way to 0.9, or right before 1, the greatest integer less than or equal to any input between 0 and 1 should always be 0. Now, what if I did this, f of 1.1? What's the greatest integer less than or equal to 1.1? If you think about it, the greatest integer less than or equal to 1.1 is 1. So what we're starting to notice is, here's how it looks, and that's why it gets the name step function. At 0, it's 0. At 1, so what do I know? The greatest integer less than or equal to anything between 0 and 1 is always just going to be 0. And then at 1, we're going to put an open point, because what is it that we noticed? The greatest integer less than or equal to 1 is 1 itself. And this is a y value of 1. So from 1 to 2, my y values are always going to be 1. And then after 2, what is it going to do? It's going to bump up to 2, and it's going to work its way up. So, and it's going to continue doing this. Now, for the negative side, let's be careful now. What if I were to do this? F of negative 0.5, which is the greatest integer of negative 0.5. What's the greatest integer less than or equal to negative 0.5? So let's think about this. What are the integers less than negative 0.5? It's negative 1, negative 2, negative 3, and so on. So the greatest integer is negative 1. So what is it that we're noticing? From negative 1 to 0, it'll be like that. And then guess what? From negative 2 to negative 1, negative 2 will be negative 2, and all the way to negative 1 it'll stay negative 2. And so that's what the greatest integer function looks like. It's like literally a step function. How come? Because this is forcing us, this notation is forcing us to take integers, right? It keeps saying, hey, from whatever number we put, what is the greatest integer less than or equal to this? And that's why we get this step function, okay? Which, that's something classic. You'll see that in calculus quite a bit as well. So get used to it. I will use it quite a bit in our class as well. Okay, so those are the functions, the graphs that we need to make sure we know, and we'll elaborate on them as time goes on. Okay, but as always, make sure to ask me questions if you have any questions regarding these notes.